So we'll do first order methods for optimization, basically gradient descent based methods in this lecture. And after that, I'll show you a little demo of how to use MATLAB's fmincon for constraint optimization problems. So we begin with gradient descent. We have a function f to be minimized, and we don't have any constraints. And let x be the current value, a known value in the domain of the function f. And let x star be the unknown minimum. We want to minimize the function f, remember. Now, assume that x star equals x. We have, this is a known value. Numerically, we have the value of this. And x star, which is the actual minimum of f, is at a distance delta x away from this point x. Okay, and so let's look at Taylor series approximation. F of x star, which is the minimum, is f of x plus delta x, which is up to the second order terms. It is f of x plus delta, del fx transpose delta x plus half delta x transpose del square fx delta x. If delta x is small enough, that is, in other words, if x is close enough to x star, then this is a great approximation because we can neglect the higher order terms. And this gradient here is what was I saying? This is the gradient del of f of x, and this is the Hessian del square f of x, the Hessian matrix. Okay, and our goal is to find this difference between x star and x. We want to find delta x so that f of x plus delta x is minimized. Okay, that's what we want to find. Okay, we're not going to find the minimum with respect to x in this Taylor series approximation. Since x is known, we just want to find delta x, and then x plus delta x will give us x star. Okay. Now, in gradient descent, the first thing that we do is we don't make use of the Hessian. Let's assume that the Hessian is alpha inverse times the identity matrix. We don't have any knowledge of the Hessian in first order algorithms. In the second order algorithms, we will use the Hessian. Okay, so we replace the Hessian with alpha, 1 over alpha times the identity matrix, where alpha is some small scalar, or some scalar. It is a small value, actually. So this is what we have. When we replace the Hessian with 1 over alpha times the identity matrix, this is what we have. And remember, we now need to minimize this function with respect to delta x, right? X is numerically known. Okay, so we take the derivative of this with respect to delta x. Don't get confused here. Okay, this is fixed. Since x is a fixed point, this gradient is a fixed value. Okay, so differentiating this with, and since it must be a minimum, the derivative of this fx plus delta x must be 0 at the minimum. Okay, and so this is a constant with respect to delta x. So this is a constant times delta x. So the derivative of this is simply del f of x with respect to x. not delta x, del x f of x plus what's the derivative of delta x transpose delta x? Twice delta x, right? And therefore, the derivative of this term is 1 over alpha delta x. And that must be equal to 0. Whence, delta x equals negative alpha del x f of x. Okay, so this is the step. So we are at x. We must add delta x to it so that we get to the minimum. X plus delta x is x star. Whence x star equals x minus alpha delta, del x f of x. That's x star, correct? But that's only our quadratic approximation. Or in fact, our linear approximation, we assumed that the quadratic term Q in the quadratic, the matrix, the Hessian was proportional to the identity matrix. Okay, so that's our assumption. And so what actually happens is, since f is some nonlinear function, this x star will take us closer to the actual minimum of f. It won't be the exact minimum. So we got to apply this step several times until we actually arrive at the global minimum of f of x. So we have to apply an iterative algorithm, and in iteration k, this is the update rule that we should apply. X k minus 1 is the value of x from the previous iteration, and del x of fxk minus 1, this is the gradient at this point, xk minus 1, and then xk, the value of the solution at the next step, iteration k, will be equal to x of k minus 1 minus alpha k del x f of xk minus 1. This is the basic update rule. Okay? And alpha k is some scalar, which may be constant or which may differ from iteration to iteration. Okay? So this is the basic update rule. Okay. So f is the function to minimize in iteration k. Okay, this is the solution at the end of iteration k. Okay, so now how do I obtain xk plus 1 from it? Just like in the previous slide, from xk minus 1, we obtained xk, right? So now this is, if you look at this plot here, so this is xk, and we compute, so this is the direction of negative del f xk, the negative of the gradient. Okay, because we are trying to find the minimum. Okay, the gradient always points in the direction of maximum increase, steepest increase. So this is the direction of steepest decrease. Okay, and alpha k is the step size in iteration k. And so this is the gradient descent algorithm. Initialize x0 to something, and then for k equals 1 through infinite, I just use this convention for loops. Otherwise, I would have had to add until condition is satisfied, keep on looping, while condition not condition satisfied, and then I would have needed an extra line. To avoid that extra line, I just simply write for k equals 1 through infinity. Okay. And in practice, this would be a while loop with the actual condition for termination. So the gradient in iteration from the previous iteration is g. Okay. So xk minus 1 is the current value that we have. And we find some alpha k. There are various methods. And then xk equals xk minus 1 minus alpha k g. G is the gradient. We take a step minus alpha k g in the negative gradient direction. Okay? So this is the basic gradient descent algorithm. We can keep alpha fixed and make it very small so that we take very conservative, very small steps. Otherwise, if alpha is actually, I misspoke, alpha should be small enough, but it shouldn't be so small that we will take a lot of iterations to finally get to the global minimum. Okay. But if it's too large, then we, even if we're close to x star, the global minimum, we might overshoot. Okay, so we need to keep a good, I hate to use the word optimal, a judiciously chosen value of the step size alpha. But why use a fixed step size when we have other options? Now, this is the exact line search method. Okay, so what we are doing here is we have to take this step. Okay, this is the algorithm. We have to take this step. Now, G, the gradient is there. Okay, and so how far should we go along this negative G direction? What should alpha be? Okay, so since we want to minimize the function, okay, so let's find out alpha such that f of xk minus 1 minus alpha k g, which is f of xk here. Okay, so let's find alpha such that this f of xk, which is f of xk minus 1 minus alpha kg is minimized. Okay, that's the best possible value of alpha. And then apply the actual step. So that becomes xk. One might ask, okay, so we are minimizing this function. During the so we are stepwise minimizing this function. But how are we finding argmin here? What's the answer? We are doing an argmin operation here. So we are doing some other minimization here within this gradient descent algorithm when the objective is in fact to minimize. The difference is here we are minimizing this function of a scalar. We are minimizing it with respect to alpha. Okay, not with respect to x. Then it would have been multi-dimensional. X could be any number of dimensions. It's not a scalar. It's a vector in any number of dimensions. Okay, so what we are applying here in fixed step size is a one-dimensional minimization, line search, and you can have different methods like the bisection algorithm, so on, very simple algorithms to perform scalar minimization. Okay, so this is not multidimensional. That's why we are allowed to keep this. Any questions? Okay, and so now the point where it's minimum is actually when the way I showed it doesn't appear to be orthogonal, but in fact the negative gradient and this contour should be orthogonal, okay, at this point. at this point. And so we land up at this point here, where this blue curve and this red line are orthogonal. Okay, so that's why I added this little thing here. Visually, it didn't look like they were orthogonal to one another. Anyways, subgradient descent. Now, in the previous situation, F was convex and differentiable. If it weren't convex, then the gradient descent algorithm would have taken us to a local minimum. Okay, if it's convex, then it will take us to the global minimum. Okay, now this is from lecture B1. If f is a convex and differentiable function, this is f, then the derivative, if f is convex, or if and only if f is a convex function, then for 2 points x and y, f of x, we are looking at two scalars here, f of x plus derivative of f of x, y minus x, should be less than equal to f of y. This is one of the possible tests for convexity. If this is everywhere satisfied for any values of x and y, if this is satisfied, then the function is convex. Okay, and graphically, this is what we saw. Now, for multidimensional cases, given any 2x and y in the domain of the function, fx plus the gradient of fx transpose times y minus x should be less than equal to f of y. Okay, this is the transpose of the gradient. So this del f of x is the gradient. Okay. Now, what if f is not differentiable? It's convex, but not differentiable. So in this case, if there is a g at this point x, if there is some g, some vector g that satisfies this condition, then g is called a subgradient of f at the point x. Okay, in fact, that's what I did. I replaced the gradient at the point x with the subgradient at the point x of the same function. Okay, so what is the subgradient? For the differentiable case, the subgradient is the same as the gradient. If at the point x, the function is differentiable, then this subgradient is in fact the gradient. So a differentiable function, if the function is differentiable at the point x, then it has a unique subgradient at the point x. And that unique subgradient is actually the gradient. For a non-differentiable function, now this is still a convex function here. Okay, and now this g here, this direction here, this slope, this, if you're looking at one dimension, the slope of this gray line would be g. Then in the scalar case, it would be simply a scalar. Anyways, so but otherwise it will give us a direction in multiple dimensions. So if this property holds, then G is a subgradient, but it's not unique. We can have multiple subgradients here when it's non-differentiable. Okay, I don't know, I thought I had this slide here. Yeah, so over here. So this g is not unique. See, at this point, this function is not differentiable, right? At this point, x. So we can draw lines in several different with several different slopes, which will always stay below this blue curve, the function, right? So the subgradient is not unique. Here's an informal illustration. So we have this cup, and this is a smooth surface, right? And here it has an edge. It's got a corner or edge somewhere here. Okay, now here, at this point, this is the, we can obtain the gradient, right? So this is the point of contact between this blue cup and this brown plane. And this would be unique. There would be a unique point of tangency at this point, right? But on the other hand, since we have a it's non-differentiable, it's not smooth at the edge here, we can have multiple solutions, right? At this point, there are many planes that can be tangent at this point if it's on the corner. I hope this was a good enough argument. I couldn't find anything better than this. Anyway, so the set of all subgradients is del G. This is the notation. And that's called the subdifferential of F. Okay, at any given point x. So this subdifferential del G is the set of all subgradients of F. Now, the subdifferential is a set, right? It's a convex set. So if G1 and G2 are two subgradients, they must be contained in the subdifferential, then for all theta between 0 and 1, then any convex combination theta G1 plus 1 minus theta G2 must also be a subgradient. So it also must be part of the subdifferential. Okay, that's what we mean by the subdifferential being convex. So here at this point, everywhere else the function is continuous, so we have a unique slope. But here, anything from this arrow to this arrow, in fact, this whole range, all arrows in this pointing upwards like this, all the way to pointing downwards like this, they're all subdifferentials. Oh, excuse me, subgradients. And the set of all these arrows is the subdifferential. Okay. And in the next lecture, we'll do some more examples. So don't worry. Okay, now, first order optimality conditions for continuous convex differentiable functions is x star a global minimum. The necessary condition was del f of x star equals 0. The gradient must be 0, correct? For the non-differentiable case, it's still continuous, but non-differentiable, still convex, non-differentiable function. What's the corresponding necessary condition? X star is a global minimum. 0 must be, the 0 vector must be in the subdifferential at the point x star, which means that 0 is also a subgradient, which means that, going back to here, this corner here you see right here, in fact, is the minimum, right? Of this blue plot of the function f. This blue curve represents the function f of x. And as you can see, this corner is actually the global minimum of this function, correct? So what do we mean by this condition? 0 belonging to subdifferential. The 0 vector would be horizontal here, right? Something with a slope of 0, a straight line with a slope of 0. So that is, in fact, in our figure, a subgradient. 0 is a subgradient. Okay, that's why this corner point is a minimum, the global minimum of the function. This is the necessary condition. Now, here's an example of a subgradient. F of x is absolute value of x. We're looking at a scalar x. So this is absolute value of x, this blue curve here. When x is negative, x is less than 0, then it's negative of x, right? It has a slope of -1. And when x is positive, then f of x has a slope of +1. F of x is x here, and f of x is minus x when x is negative, right? So the slopes are, the gradients are -1 when x is less than 0 and +1 when x is greater than 0. When x is exactly 0, anything between -1 and +1 would be a subgradient, correct? In fact, 0 is the minimum point here. Okay? Here is another example. F of x, so is equal to max I of AI transpose x plus bi. This must be a bold, non-italic x. Okay, we're looking at vectors here. Now, if you're looking at scalars, then this is max I of AIX. A would be a scalar too, okay, which would be a slope. So we have a lot of lines indexed I. Line 1, line 2, line 3, line 4, and so on. Okay, these are all the lines. If this, what I've done here is I've assumed here it's a scalar and here that we're looking at vectors. But let's assume that x is a scalar everywhere, okay? So this is the function f of x. So these are the lines. First line, second line, I equals 1, I equals 2. For some index I, this is the line AI x plus bi equals 0. Okay, so these are the different, or sorry, not AIX equals bi, but AIX plus bi. Okay, these are the different functions. And what we do is, at each point x, we take the maximum. So this is the maximum. And then from here to here, this is the maximum. This line dominates, so it's the maximum. And from here to this point, this is the maximum. This line, and then from negative infinity to this point, this is the highest maximum. Okay, so this is in fact our function in one dimension. So our subgradient would be, this is a convex function, correct? Now, what would be the subgradient at any given point? Suppose we have a point, let's say xk minus 1 is a given point. What's the subgradient at this point? what's the gradient of this line, the slope of this line, in since we're looking at one dimensions? AI, right? Is the slope of this line.
Yes.
Yes, AI.
So AI is the gradient, which is also the subgradient here because it's continuous. At this point, what is the subgradient? Where this line and this line, these two lines here are intersecting. Not these two lines, sorry, these bottom two, these two lines are intersecting at this point. So here, what's the subgradient? Or maybe here, what's the subgradient? It's a point of intersection of this line here and this line here. What's the subgradient at this point? Any line with a slope between this, the slope of this line and the slope of this line, right, can serve as a subgradient. The slope of that line would serve as a subgradient. So we can have any slope between this slope and this slope. Okay, so G equals AI, where I equals argmax. So when in the continuous case, this is when f of x is continuous at this point, then this is unique, correct? And when it is not unique, like at this point, so this argmax I would return two possible values, right? This and this. Agreed? Okay. Am I clear, or do you need some explanations here? So at a point where the function is continuous, we consider that line, and the slope of that line is in fact the gradient, the subgradient or the gradient. But it's discontinuous at this point. Okay. And so we can take this AI, and that would serve as one possible subgradient. And this AI, this A and this A, both would serve as subgradients, right? Because argmax won't be unique here at this point. Oh, argmax is actually unique. It's not the argmax. So let's look at this point. Okay, so argmax is not unique, that this line or this line. So anything between this line would be a subgradient. Sorry, I wasn't clear. I used this point instead of this point. This point is not part of this function. So this is the subgradient algorithm. Okay, I'll explain, I'll give you better examples in the next lecture, okay? So we do an initial guess, and this is the subgradient algorithm. What we do is we find a subgradient here. Okay, now we have to do one more operation here, and I'll explain it more clearly in the next lecture. I'm in a hurry for the MATLAB today. So we can have, if this point is, at this point, the function is not differentiable, then we can have multiple negative G subgradients, right? And so we have to take a direction along the negative subgradient. Okay, so what we do is, in fact, in the subgradient algorithm, we have another step. We keep track of the minimum, because we might actually land up, since we have so many different directions, we might land up with a higher value of the function. It might take us in a wrong direction. Okay, so we take the subgradient, and then what we do is we apply the step, and then x min equals, we keep track of x, we store x min. We keep track of the minimum that we found so far. Okay, and assume we are at the global minimum, and we still have possible subgradient direction. And what if we identify a subgradient direction and go further away, right? That's why we keep x min here. And so after the algorithm terminates, x min would be our solution, not the final value of x infinity. Now, projected gradient descent is like this. Now, suppose K is a convex set, and we have this. Y is a projection of the point X onto K equals argmin Y belongs to K of this L to norm Y minus X. So Y minus X, the distance between Y minus X we want to minimize. So X is any point. X could be outside the convex set. Okay, this is our convex set, the blue region. This is a point X here. Okay, and we want to find a Y in this convex set that's closest to X. Okay, so this is our point Y. And in fact, I don't want to mention this orthogonality at this point, but this is the point Y that is closest to X. And so this is the projection of X onto the convex set. So in the projected gradient descent algorithm, we are looking at a constrained optimization problem. So we want to minimize some function f of x subject to x belongs to k. So now k is our feasible set here. This is the feasible region. Okay. And so we are at xk minus 1. What we do is we apply the gradient descent step. So we get to this point y. Okay. But y equals xk minus 1 minus alpha times g. Okay, so we find this point y, but this is not feasible. So what we do is then we project y onto the feasible set. Okay, that's our new step or new x at k, iteration k. Likewise, at this iteration k, these are the contours of the function. So the gradients are orthogonal to these contours. Okay. So at this point, xk, again, what we have is, so this is a contour level set of the function at xk, and the gradient is orthogonal to it. So we find the gradient, and then we arrive at some other y here, and then project that onto k here again. So this is our xk plus 1. And you can see that gradually it will converge to x star. So this is the projected gradient descent algorithm. Here's a simple example for projection. A projection, this is the set k, norm of x equals 1, unit circle. So we want to minimize this, let's say, quadratic function, half x transpose qx, subject to norm of x equals 1. Okay. How do we apply the projected gradient descent algorithm? So the projection of x, any point x, onto the unit sphere is equal to simply this, x divided by x norm. Okay, so let's say we have a fixed step size alpha. The gradient is this, right? The derivative of f of x is del f of x is qx. So this is what we apply in each iteration. Y equals, we are at xk minus 1 at iteration k minus 1. And so xk minus 1 minus alpha q, alpha is the step size, q xk minus 1. This is y, correct? And so we can simplify this to I minus alpha q times xk minus 1. So we find y using this expression here. And then what we do is xk would be the next value of x. That would be simply, this is our y, right? So replace x with y. And so how do we project y onto the unit circle? Here, we simply divide y with, which is this, by its norm. And that gives us xk. And we apply this process iteratively until we converge to the minimum. Okay? Any questions with this? Okay, so now let's move on to the MATLAB demo of fmincon. So I define a function. This is a function handle. The function to be minimized is this. Okay, what I just highlighted here. So this is the function to be minimized. Negative x of this. So this is negative of the Gaussian, and I just added a little term to it. Okay. I just added something so that it'll look more interesting. Make it yes. And then I have, so this is a handle to my objective function at x of this. You write the objective function like this. Then the fmincon supports inequality constraints like this. So you must define A and B, and these are the linear inequality constraints. A star x is less than equal to B in fmincon in MATLAB is the inequality, linear inequality constraint. And this A can be a matrix and this can be a vector too. Okay, not in my simple example, but in general it might be. And we also have an equality constraint. The equality constraint is this. We must have a linear equality constraint, A EQ star x equals BEQ. This is the linear equality constraint. Now, what if we are trying to minimize a constraint, minimize a function which does not have linear inequality or linear equality constraints? Maybe it doesn't have this. Then we can simply replace A and B with empty sets. Okay, we can write A equals the empty set, B equals the empty set, and that will work. And then likewise for the equality constraints. And then we must have upper bounds and lower bounds. I've used scalars here But in practice, if I'm looking at two-dimensional cases, here I'm looking at two-dimensional x's. So this actually must be, we must specify lower bounds for each dimension. Okay, so since -2 is the lower bound for x1, each component of x, I can uh, specify, I can write this as -2, -2 are would be the actual lower bounds. Okay, but I'm specifying it this way, and what I'll do instead is, so this is my objective function. Just ignore this dot everything. I'll invoke some kind of a optimization algorithm. Okay, so gradient, and this will be the dual, and output, I actually don't know what this is. Put tilde here, fmincon. Okay, now let's run this algorithm. And okay, so this is the function. What happened here is how do I? This is the problem. So this is the function actually in two dimensions. Okay, and we want to find the minimum of this function, but with some constraints, correct? And so this is the contour plot. So how do I maximize this? Anyway, so what I've shown here is, let's see what the solution is. The solution would be, I invoked fmincon. I pass the handle to the function, initial guess, the starting point, then A, B, A equal, B equal, lower bound, upper bound, and then nonlinear constraint. Let's not get into that here. You can read it up on your own later on if you have to use it in this, even in this course. And options I'll get to later. So what happens is, this is how we invoke fmincon, and it returns so many things. The first thing it will return is, in fact, if that's the only thing that I wanted, I would have just written x. Okay, but x is the solution, and it's 0.16.42. And in fact, in this plot here, this, you see the star here. What color should I use for this star? Maybe I'll use, put a black is K, I think K dot on top of it, and that will work. Let's see. I think this looks a little better. So this is the actual solution. Okay, this is, now if I were to remove this, let's make it 0, 0, 0, and run it again, and then see. I could take it there. 0, 0. Oh, we must satisfy the constraints, but maybe I'm plotting it wrong. Maybe that's what's happening. I didn't plot it correctly. Maybe these, just ignore these straight lines. Let's see if that's the problem. Anyway, so this is our solution. Okay, and let's find out why. So this is our solution. 0.1429, 0.42, 0.43, 0.14 and 0.43. Okay, so we must satisfy the constraints A equal star X must be equal to B equal, right? B eq, correct? So I was drawing the lines wrong. Okay, so this is the linear equality constraint. What about the linear inequality constraint? A star X must be less than or equal to B. So A star X, and what's B? A star X is less than or equal to B. So this is the optimal point. It satisfies both the constraints, the linear equality and linear inequality constraints. Okay, now let's make change it. Maybe this should be equal to 2. And now local minimum bound that satisfies the constraint. We have a new value of what did I do? Oh, this was an inactive constraint. At the original solution, it would give what was A star X, 0.5714, right? So it's an inactive constraint. Now let's make it, instead of that, let's make it 0.25. Okay, and now let's run it. So now we get a different minimum. Let's see if both the equality and inequality constraints are satisfied. A EQ star B EQ. Oops, sorry. Star X is 1 and B EQ is 1. Right? So equality constraint is satisfied. A star X is now A star X is 0.25. So this is now the active constraint. Well, the equality constraint is always active, but this constraint now is also active. Okay, now let's look at what this options. I have specified options here. This options, it has so many fields in it. Display, final. Okay, that's why it's displaying this. It gives this message. If I write display off, and then run it, then it won't give it. These are warnings. Okay, what I can also do is set warning off. Okay, so no warning. So it gave me this point. Now, there are other things here. You can read through most of them, but the one, yeah, max iterations and max function evaluations. So sometimes it might not converge if the function is, let's do this. Display off, and then max iterations 6, only 6 iterations. Okay, that might not be enough for fmincon to converge. Well, it actually did. And the other thing is max. I don't know the details of this, but one doesn't have to. The other is max function evaluations. Function, and let's keep this at 5. Maybe now it won't converge. Okay, now what you can do is, well, since I have warning off, it didn't give, it didn't provide any okay. So it's still giving a, what is it? Yeah, it didn't converge. And so what you can do is you can look at this exit flag. This is the value of the function. Fx, the second argument that it passes is the value of the function. Okay, and x, this is the exit flag. The exit flag should be +2, something positive, for it to converge. It means that if an exit flag is positive, that means the fmincon found the minimum. Okay. Otherwise, if it could not converge within those 6 iterations, then exit flag x FLG would be non-positive. So what does exit flag mean? I'm not exactly sure, but you have to look specifically for this algorithm, interior point algorithm. What does exit flag 0 mean? Okay, now let's provide what max larger number of iterations and a larger number of function evaluations, the number of times it does function evaluations. Now, exit flag would be something positive. It's 1. Okay, and x is this. What's the value of the function fx? -4874, right? But if we did, let's say if we did 20 iterations and 20 function evaluations, honestly, I've forgotten what's the, I know that function evaluations would be more than max iterations, but I don't know the details. Anyway, let's run it again and see what happens. What's fx? Okay, it's didn't converge to this, right? 4874. It's close enough. So 20 iterations is pretty good, but it didn't converge. Let's look at x exit flag. It's 0. Right? Now let's give it 2 iterations and 2 function evaluations. Then what will happen? Oh, practically nothing. So what's exit flag is 0. It's not positive. Okay, and what's fx? -1. It's even worse. Oh, yeah, fx is even worse. How is that? Oh, because the constraint fx is -1, it's below this, but the constraints are not satisfied. X is to 0, 0, and 2. So let's say 5, 5. And by the way, let's look at exit flag 0. Okay, it got here. What's x? This is x. And what's the value of the function? -0.9, which is lower than this. F of x was at the global minimum, at the constraint minimum, it was negative 46 to negative 0.4874, right? That's the actual solution. But here it's even lower than that, but the constraints would not have been satisfied. A star x and A star x must be less than equal to B. Okay, this constraint was satisfied. What about A EQ star x? Yeah, and B EQ. So this condition is not satisfied. Okay. So guys, did you guys follow everything that I said so far? How to use fmincon?
Yes, it does. It's clear.
And for non, I actually excluded this, didn't get into nonlinear constraints. Okay, for this course, probably might not need it, but who knows. Okay, in which case, do we have any questions?
No.
So in that case, let's stop for today. And where was I? This is the problem when I get to this. Oh man.
Dr. Das next lecture is going to be at 6:30.
Yeah, we'll do you want to talk right now?